More than 2,000 years ago, a man in the city of Syracuse drew shapes in the sand and imagined the inner workings of the cosmos. That man was Archimedes, mathematician, physicist, engineer, and inventor. His discoveries shaped the very foundations of science and technology, and his legacy continues to ripple through time. From the formulas we teach in classrooms to the ancient mechanisms discovered in shipwrecks, like the Antikythera device, often called the first analog computer, his ideas echo in every discipline touched by logic and precision. This is the story of a mind that never ceased to explore, to question, and to reveal the hidden patterns of the universe. Archimedes was born around 287 BCE in the city of Syracuse, a thriving Greek settlement on the island of Sicily. At the time, Syracuse was a cultural and intellectual beacon in the Mediterranean world. His father, Phidias, was an astronomer, and though little is known about him, it is likely that his interest in the stars and celestial patterns inspired Archimedes' early curiosity. Surrounded by the mathematical and philosophical traditions of ancient Greece, young Archimedes grew up in an environment that nurtured inquiry and observation. Even as a child, Archimedes showed a remarkable fascination with numbers, shapes, and mechanics. Local stories would later describe him as a boy obsessed with puzzles, often found sketching figures in the sand or crafting rudimentary machines from simple tools. While many legends about his youth have likely been embellished over time, they reflect a truth about his exceptional mind, an innate ability to see patterns and solutions where others saw chaos. Syracuse itself played a crucial role in shaping his early development. Positioned between the Greek mainland and the Carthaginian world, the city exposed him to a wide range of ideas, tools, and engineering feats. From the harbor docks to the busy marketplaces, he witnessed firsthand how geometry and mechanics influenced daily life. These impressions would later echo in his most groundbreaking inventions. The seeds of Archimedes' scientific genius were sown early, through both family influence and the intellectually vibrant environment around him. His childhood laid the foundation for a life of discovery, a journey that would bridge abstract mathematics with practical innovation and elevate him to the ranks of the most brilliant minds in history. Eager to deepen his understanding of the natural world, Archimedes left Syracuse as a young man to study in Alexandria, Egypt, a flourishing hub of intellectual pursuit. The city's famed Library of Alexandria was the epicenter of knowledge in the ancient world, drawing scholars from across the Mediterranean. There, Archimedes encountered a wealth of Greek scientific and mathematical texts, as well as minds that would challenge and refine his thinking. During his time in Alexandria, Archimedes was likely influenced by prominent figures such as Conon of Samos, a mathematician and astronomer known for his work on conic sections and celestial mechanics. Though no direct mentorship is documented, their intellectual circles overlapped, and the impact of Alexandrian thought is visible throughout Archimedes' later writings. It was in Alexandria that Archimedes first engaged with rigorous formal geometry and began developing a structured approach to mathematical problems. The axiomatic method pioneered by Euclid resonated deeply with him. He adopted and expanded on these techniques, building a reputation among his peers for his precision and originality. Archimedes' early work explored basic geometric principles and laid the groundwork for his fascination with volume, area, and balance. He was drawn not only to abstract theory, but also to the mechanics of the physical world, how things moved, floated, or held their weight. This duality between theory and application became a hallmark of his life's work. Though Archimedes would eventually return to Syracuse, the foundation built during his time in Alexandria remained with him. It shaped his analytical mindset and gave him the intellectual tools to bridge the gap between mathematics and engineering, between the ideal forms of the mind and the concrete realities of the world. Upon returning to Syracuse, Archimedes was welcomed not just as a native son, but as a rising thinker whose education in Alexandria had elevated his stature. Although no formal academic institutions existed in the city, Archimedes continued his studies independently, often supported by the royal court of King Hero II. The king, intrigued by Archimedes' intellect, occasionally sought his help with practical problems, linking the mathematician's early career to the needs of the state. One of the first recorded challenges Archimedes faced involved determining whether a golden crown commissioned by King Hero had been fraudulently mixed with silver. Archimedes famously solved this by observing the displacement of water when he submerged the crown, giving rise to the principle of buoyancy that now bears his name. While this story has taken on legendary proportions, it marks a pivotal moment in his life, the application of theoretical knowledge to a real-world problem. Despite his growing reputation, Archimedes often worked in isolation. His methods, deeply logical, abstract, and sometimes ahead of his time, were not always appreciated by contemporaries focused on more practical or immediate concerns. Furthermore, the line between science and superstition was often blurred, and his intellectual pursuits were occasionally met with skepticism. Yet these challenges did not deter him. Instead, they forged a resilience and clarity of purpose. Archimedes began to write formal treatises, organizing his thoughts in ways that future mathematicians would find both inspiring and revolutionary. He started to develop devices for lifting water and experimented with levers and pulleys, laying the groundwork for his mechanical innovations. In these formative years, Archimedes navigated the tension between visionary thought and societal expectation, emerging not only as a thinker, but as a practical genius capable of solving problems that others deemed unsolvable. With his reputation growing in both Syracuse and intellectual circles abroad, Archimedes began producing the first of many groundbreaking works that would shape the course of science and mathematics for centuries. Among his earliest written contributions were treatises such as On the Sphere and Cylinder, in which he derived formulas for surface area and volume with unprecedented precision. In doing so, he surpassed previous Greek mathematicians in both depth and method. One of his most celebrated early insights came from his studies of levers and mechanical advantage. It was during this period that he famously stated, "Give me a place to stand, and I will move the earth." While the quote may be apocryphal, it reflects the essence of his revolutionary understanding of force and motion. Archimedes did not merely theorize. He showed how abstract principles could be used to engineer real-world solutions. At the request of the king, he also invented the Archimedean screw, a device used to raise water efficiently. Originally intended for irrigation, this screw became one of his most widely applied inventions and is still used in some parts of the world today. These early accomplishments established Archimedes not only as a mathematician, but as a master of applied science. His ability to bridge geometry, physics, and engineering set him apart in an age when such interdisciplinary thinking was rare. He was beginning to demonstrate a pattern that would define his career: deep theoretical work paired with extraordinary practical utility. Through his writings and inventions, Archimedes was already reshaping how people thought about the physical world. His contributions marked the beginning of a legacy that would echo far beyond the shores of Syracuse, into the annals of history and the very fabric of modern science. As Archimedes entered the most productive phase of his life, his intellectual brilliance reached unprecedented heights. His treatises became increasingly ambitious, tackling problems that would remain unsolved for centuries without his methods. Among his most profound works was on the measurement of a circle, where he devised a technique to approximate the value of p with remarkable accuracy, estimating it between 3,1,7 and 3,10,71. This was a mathematical feat far ahead of its time, relying on geometric reasoning using inscribed and circumscribed polygons. On floating bodies, Archimedes laid the foundations of hydrostatics. There, he formally articulated what is now known as the principle of buoyancy, stating that a body immersed in a fluid experiences an upward force equal to the weight of the fluid it displaces. This principle became the cornerstone of fluid mechanics, crucial to the development of naval architecture and engineering. Archimedes also delved into the concept of the center of gravity, helping future generations understand balance, stability, and motion. His work, The Method of Mechanical Theorems, a manuscript lost for centuries and rediscovered in the 20th century, reveals that he anticipated elements of integral calculus by using infinitesimals to determine areas and volumes. In addition to theoretical breakthroughs, Archimedes designed machines that were both practical and ingenious. These included compound pulleys for lifting heavy weights and various war machines, such as catapults and defensive devices, some of which would later become legendary during the Roman siege of Syracuse. The fusion of profound mathematical insight with ingenious mechanical invention defined Archimedes' genius. He was not content with abstract speculation. His work was deeply rooted in understanding how the world works and how that understanding could be applied. His discoveries not only pushed the boundaries of ancient science, but also built a foundation for modern physics and mathematics. During his lifetime, Archimedes' reputation extended far beyond the city of Syracuse. His writings circulated among scholars in the Greek world, particularly those in Alexandria, where intellectual exchange was vibrant and well documented. Although he lived relatively far from the academic centers of the Hellenistic world, his treatises earned admiration for their clarity, rigor, and originality. He was known not only as a brilliant thinker, but as a craftsman of ideas, someone who could elegantly solve complex problems with precision and logic. King Hero II of Syracuse continued to support Archimedes, recognizing the value of his intellect, not just for science, but for the state. Archimedes frequently advised the king, particularly in matters of engineering and defense. His devices for lifting and transporting heavy objects improved construction techniques, while his water screw became vital for irrigation and agriculture in the region. The scholar's prestige also drew correspondence from mathematicians and philosophers in Alexandria, who saw in him a master of the geometric method. His writings were often framed as letters to friends and colleagues, such as Dositheus and Eratosthenes, providing insight into the scientific dialogues of the time. These relationships ensured his discoveries were preserved, debated, and admired. Within learned circles, despite his acclaim, Archimedes remained humble and devoted to the purity of inquiry. He reportedly regarded his theoretical achievements as far superior to his mechanical inventions, believing that understanding the nature of things was a nobler pursuit than crafting machines. Yet even in his modesty, he recognized the utility of his ideas when applied to practical problems. In his own time, Archimedes stood as a rare figure, both a contemplative mathematician and a pragmatic inventor. His dual legacy made him an invaluable asset to Syracuse and a luminous mind within the broader Hellenistic world. Despite his towering intellect, and celebrated achievements, Archimedes' path was not without difficulty. One of the greatest challenges he faced was the isolation that came from living in Syracuse, far from the bustling intellectual exchanges of Alexandria or Athens. While his writings reached those distant centers, the lack of immediate peers limited opportunities for real-time collaboration or debate. For a thinker of his magnitude, this distance was both a blessing and a burden, offering solitude for deep reflection, yet also a sense of intellectual seclusion. Archimedes also encountered resistance from those who failed to grasp the value of theoretical science. While practical inventions garnered praise, his abstract mathematical pursuits were sometimes misunderstood or dismissed as overly obscure. This divergence between public perception and personal passion created tension. Though celebrated for his mechanical prowess, Archimedes often lamented that his true joy, pure mathematics, was less appreciated. A significant obstacle came in the form of geopolitical instability. As the Roman Republic expanded its influence across the Mediterranean, tensions rose between Rome and Syracuse. Eventually, during the Second Punic War, Rome laid siege to the city. Archimedes, though well into his later years, played a vital role in Syracuse's defense, designing war machines that astonished Roman forces, giant cranes to lift ships, catapults with unmatched precision, and even mirrors, according to later accounts, that could set ships ablaze with focused sunlight. These inventions, though effective, could not prevent Syracuse's eventual fall. In 212 BCE, the Romans breached the city. Despite strict orders from the Roman general Marcus Claudius Marcellus to spare Archimedes, a soldier, either unaware of his identity or indifferent to the command, killed him. According to tradition, Archimedes was absorbed in a geometric problem at the time and refused to leave his diagrams. His death marked a tragic end to a life devoted to knowledge, one silenced not by nature, but by the violence of war. In the final years of his life, Archimedes remained intellectually vibrant, even as the political climate around him grew increasingly volatile. With Syracuse caught between alliances in the Punic Wars, the tension in the city was palpable. Yet Archimedes persisted in his work, driven by a passion for understanding the universe that never wavered. During this period, he continued to produce some of his most insightful writings. His treatise, The Sand Reckoner, is a striking example. In it, Archimedes sought to estimate the number of grains of sand that could fit in the universe, a bold conceptual leap that forced him to develop a new numerical system capable of expressing astronomically large numbers. Far from a whimsical exercise, the work reflected his desire to expand the limits of human thought and explore the vastness of the cosmos with mathematical rigor. Though surrounded by the reality of impending war, Archimedes' writings from this time show little concern for politics. His focus remained squarely on intellectual pursuits, geometry, mechanics, astronomy, and the principles governing balance and motion. He returned frequently to the themes of equilibrium, symmetry, and proportion, seeking clarity and harmony in a world that seemed increasingly chaotic. It is said that Archimedes requested a simple image to be engraved on his tomb, a sphere inscribed within a cylinder, symbolizing his favorite geometric proof, and perhaps his deepest pride. The choice reveals much about the man, not a warrior or public figure, but a mind committed to the abstract elegance of truth. Though the siege of Syracuse loomed, Archimedes' final contributions were not shaped by fear, but by the enduring flame of curiosity. He died as he lived, immersed in thought, guided by reason, and devoted to uncovering the secrets of nature. Archimedes' death did not extinguish the brilliance of his work. On the contrary, his writings and inventions resonated through the centuries, laying the groundwork for entire fields of study. his contributions to mathematics, physics, and engineering became essential references for later scholars in both the Islamic Golden Age and the European Renaissance. In mathematics, Archimedes pioneered methods that anticipated integral calculus nearly 2 millennia before Newton and Leibniz. His approach to calculating areas, volumes, and centers of gravity introduced the concept of infinitesimals, a tool that would become foundational to modern analysis. His works, such as On the Quadrature of the Parabola and The Method, inspired future mathematicians to explore the limits of geometry and mathematical reasoning. Mechanically, Archimedes left a legacy of practical ingenuity. Devices like the Archimedean screw were adopted widely for irrigation and remain in use today in various forms. His studies on levers, pulleys, and balance systems became the basis of classical mechanics, formalized centuries later by Galileo and Newton. The principle, the power to move the earth, found real-world application in countless lifting and transportation technologies. Perhaps most intriguingly, his influence can be glimpsed in later ancient engineering marvels, such as the Antikythera mechanism, a complex geared device discovered in a shipwreck off the Greek coast. Dated to around 150–100 BCE, it is considered the first known analog computer, capable of predicting astronomical events with remarkable precision. Though there is no direct evidence linking Archimedes to its construction, its sophistication echoes the kind of mechanical and astronomical ingenuity described in ancient accounts of his inventions. It stands as a powerful testament to the scientific legacy he helped inspire. In the Islamic world, scholars translated and preserved Archimedes' works, recognizing his mastery of both abstract reasoning and practical engineering. These texts re-entered Europe through Arabic translations, igniting intellectual revival in medieval universities. During the Renaissance, figures like Leonardo da Vinci and Galileo Galilei celebrated Archimedes as a paragon of scientific genius. His influence is evident in the scientific method itself, an approach that blends observation, experimentation, and mathematical proof. Archimedes' legacy is not only found in formulas and machines, but in the spirit of inquiry he embodied. He showed that profound beauty lies in understanding the world, not through myth or mysticism, but through logic, evidence, and the unwavering pursuit of truth. More than 2,000 years after his death, Archimedes remains one of the most iconic figures in the history of science. His ideas continue to inform disciplines ranging from mechanical engineering to theoretical physics, from fluid dynamics to computer science. The clarity and elegance of his reasoning have made him a timeless symbol of intellectual excellence. In modern education, Archimedes is often the first ancient scientist students encounter when studying classical physics or geometry. His principles of buoyancy and leverage are still taught in introductory science classes around the world, and his mathematical techniques, especially those anticipating integral calculus, are now viewed as essential stepping stones in the evolution of mathematics. Beyond academia, Archimedes' influence can be seen in engineering design, architecture, and modern technology. His concepts underpin machines that lift heavy loads, pumps that move fluids through systems, and even software that models physical interactions. The Archimedean spiral is used in various technologies, including scroll compressors and optical systems. More profoundly, Archimedes represents a philosophy of thought, the belief that the universe is comprehensible through logic, observation, and systematic reasoning. His life offers a powerful lesson. Knowledge pursued with passion and discipline can transcend generations, cultures, and even the limitations of time. In an era increasingly shaped by rapid technological advancement and scientific discovery, Archimedes serves as a reminder of where it all began, with curiosity, with questions, and with a man drawing diagrams in the sand, searching for the truths hidden in the patterns of nature. His story continues to inspire scientists, engineers, educators, and students. Archimedes does not belong only to antiquity. He belongs to every age that values knowledge, creativity, and the bold pursuit of understanding.